Hey everyone, and welcome. Today we are talking about one of the absolute workhorses of statistics, the T statistic. It's kind of like a secret weapon for making really big calls when you only have a little bit of data to work with. So let's just imagine for a second. You've got this big idea. Maybe it's a new workout routine that you think is amazing, or a new study technique. The thing is, you can't test it on everybody on the planet, right? You've only got a small group. So how do you know if your results are the real deal and not just some random fluke? That is the exact problem we're going to solve today. Okay, so to really get the solution, we first have to understand the traditional tool that statisticians would reach for, and more importantly, why it so often just doesn't work in the real world. Now, in a perfect world, a textbook world, we'd use something called a z-score. And honestly, it's fantastic. The z-score tells us exactly how different our sample is from the entire population. It's kind of the gold standard for checking if what you found is statistically significant. But here it is. Here's the catch. I mean, it's a really big one. Kind of the fatal flaw. To use the z-score, you need to know the standard deviation of the entire population. Just think about that for a second. If you're studying a new drug, how on earth could you possibly know that information for every single person who might ever take it? You can't. That's the thing. In the real world, we almost never have this information. I mean, if we already knew everything about the population, we probably wouldn't need to be running a test in the first place. And this is where that gold standard tool just completely falls apart. And this is why the T statistic is so brilliant. It's the hero of our story. It was designed specifically for these messy, real-world situations where our data is incomplete, which, let's be honest, is pretty much all the time. Okay, so take a look at these two formulas. At first glance, you might even think they're the same thing. And you're not wrong, they are incredibly similar. But look closely at the bottom part of the fraction, the denominator. The z-score uses that little Greek letter, sigma. But the t-statistic? It swaps it out for a plain old s. And that s is the game changer. It stands for the standard deviation of your sample. You know, the data you actually went out and collected. So the t-statistic cleverly estimates the error using the information it actually has. It doesn't need data on the whole population, which makes it an incredibly useful and practical tool. But, there's no free lunch. When you use an estimate instead of the real deal, you're introducing a little more uncertainty into the equation. So to account for that, the t-statistic has a special rule. It brings in this new concept called degrees of freedom. Now, degrees of freedom sounds way more complicated than it actually is, I promise. For a t-test, the calculation is super simple. It's just your sample size, which we call n, minus 1. That's it. So if you have a sample with 20 people, you have 19 degrees of freedom. Easy enough, right? And this chart really shows you why those degrees of freedom matter so much. A t-distribution isn't just one curve. It's actually a whole family of them. When you have a small sample and therefore fewer degrees of freedom, the curve gets flatter and the tails get fatter. So what does that mean? It means the test is being more cautious. It's saying, hey, we're working with less data here, so we're going to need a really strong result before we're convinced. Okay, so we've got the tool, we understand its special rule, so now, how do we actually put this thing to work? Well, it's actually a really clear 4-step process. Think of it like a recipe. First, you state your hypotheses. Basically, you say what you think is going on. Second, you set the goalposts. You define what's going to count as a significant result. Third, you actually do the math and calculate the t-statistic from your data. And finally, step 4, you make the call. You see if your result crossed the finish line or not. And this image shows you exactly what that looks like. Those shaded areas way out on the ends of the curve, those are your critical regions. If the t-value you calculated is extreme enough to fall into one of those zones, boom, you found a statistically significant result. You get to reject the null hypothesis, which is just a fancy way of saying the boring theory that nothing is going on is probably wrong. But hold on. Finding a significant result is actually only half the story. And this leads us to what is frankly a much more interesting and way more important question. So, the math tells you that there's probably a real effect here, that it wasn't just random chance. Awesome. But so what? Is this effect a tiny little blip that barely makes a difference? Or is it a massive game-changing discovery? Just because it's significant doesn't tell you how big it is. And to answer that question, we need to measure something called effect size. This is a totally separate calculation. It moves past that simple yes or no of significance And instead, it tells you about the magnitude, the real-world importance of what you just found. It answers the question, how much? A really common way to measure effect size is with a metric called Cohen's d, and this table here is like a handy little cheat sheet. A d-value of around 0.2, that's considered a small effect. 0.5 is medium, and if you're getting up around 0.8 or higher, well, now you're talking about a large effect. This helps put your findings into a practical context anyone can understand. And finally, when it's time to share what you've found with the world, there's a standard way to do it. You state clearly whether the result was significant or not. You report the actual T statistic, making sure to include the degrees of freedom right there in the parentheses. And you report the probability value or the p-value. This universal format lets any other researcher see exactly what you did and what you found. So when you boil it all down, that's really the magic of it. The T statistic is this incredibly powerful tool. It lets us take one small, manageable sample and use it to make some pretty smart, well-informed conclusions about the entire unknown population that it came from. It's pretty amazing. At the end of the day, that's what all of this is for. It's about having a reliable way to find a real signal in a whole lot of random noise. It's how we test our ideas and make discoveries. So the only question left is, what signals are you hoping to find? Thanks for tuning in.